Welcome to using AWS ParallelCluster to simplify HPC cluster management. My name is Nathan Stornetta, and I'm a product manager at AWS for HPC products. This session will be focused on introducing you to the tools and ideas you need to be able to run your HPC workloads on AWS with ParallelCluster, an orchestration tool available at no cost to our customers. The agenda I'll be following for this session today will be as follows. First, I'll provide an overview of HPC on AWS, what makes it compelling to customers, what our portfolio of AWS services for HPC looks like, as well as a few cases in which customers have been successful running HPC on AWS. Next, I'll spend some time introducing AWS ParallelCluster, an essential service in AWS's HPC portfolio that makes it fast and easy to set up HPC clusters. After that, I'll go through a live demo. I'll show you what it looks like to configure and run an HPC cluster with AWS ParallelCluster, submit a computational fluid dynamics, or CFD, workload on that cluster, and to use DCV, our standard tool for remote visualization and post-processing. From there, I'll share a couple of use cases and elaborate on why it is that being able to scale clusters up and down quickly can be so valuable to HPC users. Finally, I'll spend some time doing a quick overview of some advanced features and best practices for ParallelCluster that can be helpful once you've gotten started on AWS. If you find this session to be valuable or want to dive deeper into a specific topic related to some of the areas I'll be talking about today, there are a number of other workshops and builder sessions covering related material at re:Invent. I hope to be able to see some of you in person at the two builder sessions I'll be leading, CMP409R, selecting the right instance for your HPC workloads, and CMP418R, using AWS ParallelCluster to simplify cluster management. Before fully diving into talking about AWS ParallelCluster, it's valuable to understand some of the key reasons why we believe that AWS is such a fantastic platform on which to run HPC workloads. I'll explain a few of the reasons customers have been successful with HPC on AWS. I'll also explain why it is that changing the mindset with which we approach HPC is a key part of making the most of what AWS has to offer. When customers transition to running HPC on AWS, the biggest adjustment we've found they make is learning to work with virtually unlimited infrastructure. This infrastructure means you can scale very quickly and on demand while paying only for resources you use. This represents a dramatic shift from the world of on-premise HPC, in which you are necessarily constrained by the finite capacity you have available to work with in your cluster. This leftmost graphic on this slide shows how it is that in a traditional HPC environment, there's a mandate to make a significant effort to pack jobs as tightly together as possible. That's because when resources are shared across users and hardware is expensive, there's a feeling of needing to use up every last bit of capacity available at all times. In practice on-prem, though, this means wasted time waiting in long queues. It also means having to run with fewer than ideal compute nodes, or having to work with general-purpose servers instead of one specialized to each of your workloads. All of this in the name of fitting your work in alongside everyone else looking to access those same computing resources. With HPC on AWS, you're no longer constrained by needing to squeeze jobs in among those shared resources. You can choose to access as much or as little capacity as you need when you need it. Once you can skip the queues to run and rerun your jobs, you dramatically accelerate the rate at which you can experiment and iterate. Plus, you can choose the hardware you want to run your jobs on, so they're optimized to your workloads. That way you get the best possible performance on the latest computing hardware available. All of these are reasons why we like to say that a total cost of ownership analysis never tells the whole story about the value of HPC. According to Hyperion Research, 72.8% of organizations running HPC report having to delay or cancel entirely some of their HPC jobs. For all of those organizations, that means questions left unasked, experiments that are never completed, and products that can never be made. Ultimately, that means money and profits left on the table. The cost of all of those essential aspects to the business goes far beyond what could be covered by considering only the cost of hardware. Once you're running on AWS, though, you no longer need to consider these trade-offs because you always have on-demand access to the virtually unlimited infrastructure that you require. While I'll be spending most of my time today talking about one of our orchestration services, AWS ParallelCluster, it's likewise important to recognize that this is one piece of a much larger portfolio of products that are ideally positioned to be a part of running your HPC workloads. For each step of the process to migrate or run your workloads on AWS, we have products to help you with what you need. That includes data management and data transfer, compute and networking, storage, orchestration, and also visualization. Additionally, we have a number of services that span across these categories, like Amazon CloudWatch, Amazon IAM, and AWS budgets for monitoring your infrastructure, managing identity and access, and controlling your costs. Since these services span all of these categories of HPC products, they make it easy to take control of your complete HPC stack. While it would take too much time for me to go into detail about all of these services, I'll spend some time speaking later on about a few more of these services that are tightly integrated with AWS ParallelCluster to simplify the process of running your HPC jobs. By way of example, I'll also share some customers who have been successful transitioning HPC workloads to AWS and experiencing the kinds of benefits I've already mentioned. We have Western Digital, a manufacturer of hard disks and data storage products. Understanding the ability to leverage AWS's extreme scaling abilities, they were able to create an HPC cluster of 1 million vCPUs using only Amazon EC2 Spot instances. In an industry like theirs in which the speed of research and innovation matters, this meant they were able to reduce their simulation time from 20 days to only 8 hours. That freed up their research and development teams to explore new designs and innovations at a far faster pace than would otherwise be possible. As another example, Morningstar, a global provider of independent investment research and products, was able to run their financial risk models over 4,000 times faster than before. Work that used to take them months could be done instead in hours. Having AWS's Elasticity let them cover 50 times as many securities as before, expanding the amount of research and products they could offer their customers. Both Western Digital and Morningstar are examples of loosely coupled workloads. But we've also seen tremendous success in helping customers with tightly coupled clusters achieve similar levels of scale. Earlier this year in August, we saw one of our customers, Descartes Labs, build a supercomputer using AWS resources that scaled to over 40,000 cores and placed number 136 on the top 500 supercomputing list. With that as context for what can be achieved on AWS with our set of HPC services, I'll be digging into more of what specifically makes AWS ParallelCluster compelling for our HPC customers. That will make more concrete some of the benefits of HPC on AWS that I've already mentioned. To describe AWS ParallelCluster at a high level, I'll call out that it is an open source cluster management tool that's managed primarily through a command line interface, or CLI. Here, when I say cluster, this means a system with a master node, compute nodes, a job scheduler, and a shared file system. All of ParallelCluster's code is hosted on GitHub, where we also provide customers an avenue to raise issues and create their own pull requests as part of contributing back to the open source community. Any AWS customer can download the ParallelCluster tool through the Python package index, or PyPy. As orchestration software for HPC, at the highest level what AWS ParallelCluster really is a tool to help users simplify the configuration, creation, deployment, and management of HPC clusters on AWS. Three of the key benefits we've seen for customers using ParallelCluster is that it makes cluster management easy, it includes automatic resource scaling, and that it facilitates a seamless customer experience in migrating HPC workloads from on-premise environments to the cloud. This makes it a great choice for all kinds of cloud HPC, from spinning up a quick test cluster to fully migrating all of your HPC workloads to the cloud. The basic workflow for ParallelCluster has 3 core steps to make cluster management simple and easy to organize. The ParallelCluster interface includes the pcluster configure command that helps you make many of the initial decisions that are essential in starting up your cluster. This step streamlines the decision-making process for you so that you can quickly and knowledgeably get the kind of cluster you need fast. This pcluster configure process creates the initial configuration file that ParallelCluster uses in architecting your cluster. Next, depending on your specific needs, you may wish to make some more specific modifications to this configuration file, such as attaching your specific block storage or mounting your own shared network file system. All of these steps can be taken care of by adding and modifying simple parameters in your configuration file so that you can take full advantage of the granularity of options available through ParallelCluster. You can store and manage these configuration files locally on your machine and stay organized to track any number of clusters you wish to have available to you. Finally, once you have everything set up just the way you like it, you can start, stop, restart, and check the status of any one or all of your clusters using the same ParallelCluster command line interface. Because one of the fundamental benefits of AWS is its elasticity, and we want HPC customers to be able to take full advantage of it, this idea is fully baked in to ParallelCluster as well. When you submit a job through your preferred job scheduler, ParallelCluster can scale up the resources needed for that job on demand. If you submit more than one job, ParallelCluster can continue to scale up more resources to match those additional jobs too. This automatic resource scaling eliminates the need to wait for computing resources to become available. On the other hand, since you may not need to be running jobs 24/7, ParallelCluster can also scale down for you when its computing nodes are idle. When individual nodes have finished running their jobs, ParallelCluster can take those nodes offline in a safe way so that you only end up using the resources you actually need when you need them, saving you money and keeping you from needing to manually start and stop your cluster all the time. This elasticity applies to your data storage and file systems shared across your computing clusters as well. With the virtually unlimited infrastructure in AWS, you can bring even your largest data to AWS and use it in a performant and cost-effective way for HPC. Another reason customers love ParallelCluster is that it makes migrating existing HPC workloads to the cloud easier. Because the cloud is a radical departure in many ways from traditional on-premise environments, that means lots of applications can benefit, both in terms of performance and cost effectiveness, by re-architecting workloads with a cloud-native approach. Making that transition is part of an overall process, though, and that can take some time and planning. Because ParallelCluster provides an environment and tools that are already familiar to HPC users, it simplifies the first steps in this migration process, making it far easier to lift and shift your workloads to the cloud with only minimal adjustments. You can pick and choose which workloads you're ready to move to the cloud and do it at your own pace. And what's great about ParallelCluster is that because it integrates with so many other AWS products, you can transition to using more cloud-native services when you're ready from the workloads you already have running in ParallelCluster. So, when you're ready to make some or all of your HPC workloads cloud-native, ParallelCluster is ready to help you with that too, giving you a chance to get even better and more cost-effective performance than you otherwise could. As an HPC orchestration tool, ParallelCluster makes it easy to take all of the disparate and sometimes messy pieces in the HPC ecosystem and organize them into a nice package that's both flexible and easy to use. This includes everything from your operating system, your job scheduler, your choice of shared file system, your choice of data storage, your choice of networking configurations, and your MPI or collective communications library. This is before even considering the wealth of options you have available in your choice of compute nodes. And again, all of these options are accessible through the ParallelCluster guided configuration and the easy-to-use and manage configuration files that dictate your cluster's architecture. Taken together, all of these different benefits can make ParallelCluster the best choice for HPC on AWS for a number of different use cases. ParallelCluster makes it easy to take production workloads and focus on optimizing them so that they can run faster or with greater precision, thanks to the fact that you can customize your infrastructure for each and every type of job you want to run. ParallelCluster gives you the flexibility to get each of those workloads just right. Fast prototyping is likewise easy with ParallelCluster because it makes the elasticity of AWS so accessible and lets researchers and engineers testing new products experiment quickly and on demand with different configurations so that they can figure out what works best and ask more interesting questions. Similarly, something else we've heard from customers that they love about using ParallelCluster is that it lets them run workloads on short notice when there are specific business needs that demand it. And so, when they need to finish that job today in order to meet a business-critical deadline, they don't have to worry about finding space in their on-prem environment or figuring out how to set up their cluster in the cloud by themselves. Because of its flexibility and depth, we've seen customers across a wide number of industries find success in using AWS ParallelCluster. That includes life sciences, where a number of customers have run applications ranging from drug discovery, genomics, and cancer research. Financial services, where we have customers running financial risk simulations and quantitative trading algorithms. Oil and gas, with customers running reservoir modeling and seismic imaging. Design and engineering, with computer-aided engineering and computational fluid dynamics. And even climate and geosciences, with weather forecasting and climate modeling. Regardless of the industry vertical you find yourself in, the infrastructure and tooling available through ParallelCluster can help. The same is true for workloads with many different classes of characteristics. Tightly coupled and loosely coupled workloads alike run well using ParallelCluster. And while I've focused primarily on traditional HPC in talking about ParallelCluster, it's also well suited for a number of AI, machine learning, and data-intensive analytics tasks that require distributed computing functionality for training or inference. It's possible to run workloads with each of these classes of characteristics in the same or entirely separate environments you can create with ParallelCluster. Here's a brief overview of the architecture of AWS ParallelCluster to give you an idea of how it knits together its underlying services behind the scenes. You, as a user, are able to interact with ParallelCluster on your local machine by installing its open-source Python package powering the command line interface. That package can be downloaded and run on any operating system on which you can run Python, including Windows, Mac OS, and Linux. ParallelCluster takes the text configuration files you develop on your local system and translates them into an AWS CloudFormation template. That CloudFormation template is created in your account and provides the layer of infrastructure as code describing your HPC cluster. Part of that configuration will determine the region, availability zone, and subnet within which your cluster will be created as part of your own virtual private cloud network. The CloudFormation template also describes characteristics of your master server, or head node, the auto-scaling group that determines the minimum and maximum size of your cluster you'd like to have, your network file system and data storage, and finally, your compute nodes that are co-located to minimize inter-node communication costs. As a user, you are able to log into the master node via SSH, or can access it as part of a remote desktop session through the DCV service available on AWS. It's from that master node that you're able to submit each one of your jobs to the job scheduling software of your choice, Slurm, SGE, Torque, or AWS Batch. When the job scheduler on the master node sees that it needs more resources, ParallelCluster interacts with the AWS auto-scaling group and requests more. Conversely, when the job scheduler sees that it doesn't need all of its resources, ParallelCluster interacts with the auto-scaling group and reduces the size of your cluster. If you choose to log into the master node using DCV, you also have the ability to perform post-processing visualization so that you can look at and better understand the results of your workloads and simulations. And now that we've had a chance to walk through what ParallelCluster is and how it's architected, let's dive into a short demo so that I can give you a chance to see how it really works. To start, I'm going to show you how easy it is to install ParallelCluster and get up and running for the first time by using the pcluster configuration wizard. Here I am in a Python virtual environment, although you could go ahead and follow the same set of steps without being in a virtual environment. From my command line, I'm going to go ahead and use pip to pull down the AWS ParallelCluster package from PyPy, the Python package index. With that, you can see that I'm downloading all of the files that are required to be able to run AWS ParallelCluster. While I'm at it, it's also a good practice to go ahead and install the AWS CLI. This allows you to have command line access to a number of different AWS tools and resources, which can come in handy when using ParallelCluster. I'm going to go ahead and install it similarly by using pip. Okay. With that done, I now have access to a new command on my command line, pcluster. There are several different commands available with pcluster, and I'll give you a brief look at them using the pcluster-h command that opens up the help guide. This is a good first resource anytime you need a refresher on how to accomplish something with ParallelCluster. You can see that there are a number of different subcommands you can execute with pcluster. That includes creating the cluster, stopping and restarting the compute nodes, SSHing into the cluster, and logging in to a remote desktop of the cluster through a DCV session. Now that we've seen those different options, I'm going to go ahead and walk you through the process of how you would create your very first cluster by using the pcluster configure command. This command will walk you through the essential configuration options you need to get your cluster up and running. The first option we have here in configuring our cluster is to choose the AWS region we want to run in. As you can see from all of the options we have, you have a number of regions to choose from, giving you flexibility in where you want to store your data and where you'd like to have your infrastructure located. For now, I'm going to go ahead and choose US West 2, since that's a region located close by to where I am. Next, we get to choose which job scheduler we wish to use in submitting our batch jobs. Here, I'm going to go ahead and choose SGE. Next, I can choose my operating system. For this, I'm going to want to use CentOS 7, which gives me the option to use DCV, as we're going to see a little bit later. Then I can choose my desired cluster size, expressed as a number of instances or compute nodes, with both a minimum and a maximum number of those nodes. Let's say here that I'm going to want to keep my cluster up and running for a long time, and I expect that sometimes I won't really need any nodes running at all. So I'm going to go ahead and stick my minimum at 0 instances to help me save on costs. When it comes to maximum number of instances, I'm going to go ahead and put 64. That gives me a chance to scale up to a reasonable size when I really need it for my simulations, even though I don't expect to need that many instances all of the time. I can choose the instance type I want to use for both my master node as well as my compute nodes. I'm going to choose an instance from the G family that's well suited for visualization. And then I'm going to choose C5 instances that are compute optimized instances, well suited for many CFD workloads. Next, I'll specify my EC2 key pair. This is what's used for authentication and connecting to my cluster. This is something you can create separately using the AWS CLI or through the AWS console on the web. Finally, I have the option of either automating the creation of my virtual private cloud environment or choosing to exercise more direct control over where exactly I want it to sit by picking a VPC ID and a subnet. I'll go ahead this time and just let that be automated by ParallelCluster. Now that we've done that, we can go ahead and take a look at our configuration file. If we take a look, we can see how it is that this config file is organized. Here in the config file, you can see that there are a number of different section headings indicated by brackets with the relevant settings for each heading underneath. As part of the heading for each cluster, we see that there's a name given to each different cluster we want to build, so that we can keep track of settings for multiple clusters, even within a single file. We also have the option to create multiple files and pass the file name to pcluster at cluster creation time. You can see here that each of the different questions we answered during the configuration process have helped populate these different available settings. And you can see that there are some additional settings that we can use to create more advanced functionality, such as adding access to S3 to read data, or adding a post-install bootstrap action to be executed on your AMIs. Once we've finished setting all of our different options to our liking, we can go ahead and create the cluster using the pcluster create command. Because this process takes a couple of minutes to complete, I've already gone ahead and created my cluster ahead of time, so we can skip ahead to accessing our cluster. Let's go ahead and see how to log into our cluster's head node. ParallelCluster makes this easy by creating a shortcut you can use, which is the pcluster SSH command. By running this command and specifying the name of a cluster you've created, you can log in to that cluster automatically with the key pair you previously specified. I'm going to go ahead now and log into one of the clusters I've created, the reInvent cluster. Now, when I created this cluster, I used a custom AMI as part of my configuration so that I could include software I've installed previously on an Amazon EC2 instance. In this case, I've installed OpenFOAM, an open source software that can be used for computational fluid dynamics, and ParaView, another piece of open source software that can be used for visualization of CFD outputs. I've also gone ahead and uploaded a simple batch script to submit one of the example CFD jobs available as a demo within OpenFOAM, in which we model the flow of water through a dam that's burst. I'll go ahead and kick off that job by simply running a couple commands. That's all well and good. But how are we going to deal with the output and making sure that we can see the results? This is where DCV comes in. I'm going to disconnect from this cluster for the moment so that I don't have to wait for this job to run to completion. Finally, to close, I'm going to show you how it is that you can easily get a visual remote desktop useful for visualization with one of your clusters. I've got another cluster that I've already set up for DCV, and I'll show you how it is that we can connect to it from here. Now this is really cool, as you can see. You can see that ParallelCluster and DCV together make it possible to access our cluster's master node through a remote desktop. This can help users less familiar with the command line interact with our HPC cluster too. As you can also see, from here we can navigate through our file system. And we can also open up a terminal from any of these locations to run command line actions. We can also go ahead and run the ParaView command to see how it is that we can use this open source software to visualize CFD outputs. While we don't have time today to take a look at these visualizations in depth, hopefully this can give you a feel for how, with ParallelCluster, you can run your end-to-end HPC workloads from cluster creation, job execution, and through post-processing. Now that you've had a chance to see what it's like to interact with ParallelCluster, and I've had a chance to talk through the benefits of its elasticity, I want to share with you some real-life data to demonstrate how powerful the ability to scale up and down on demand can be. I'm going to tell you a brief story about Alice, Bob, and Carol. Alice and Bob are part of an engineering team designing the latest product at their company, and Carol is their boss. Alice and Bob's team has a firm deadline to deliver the final designs for their product before the end of the quarter. Alice and Bob present their design to Carol the day before the deadline, only to uncover a mistake that requires them to redo some of their work. Alice and Bob previously spent days waiting to run their models through the company's on-premise cluster. And because other teams are all facing similar deadlines, there's no way they'll be able to access enough resources again in time to rerun all of their jobs. Luckily, Alice and Bob have been starting to experiment with ParallelCluster. The next morning, Alice and Bob get in to resubmit their work together using ParallelCluster. They kick off their workloads around 8:45. Right away, AWS starts working to collect capacity to add to their cluster. They have no trouble getting enough capacity to run their jobs, to run them with modifications. 500 compute nodes running simultaneously with 18,000 cores, all available in less than 15 minutes. You can see on this chart, taken from Amazon CloudWatch, how quickly they are able to scale up and then back down. In looking at this chart, you'll see the orange line showing the number of nodes they've requested through ParallelCluster. The green line showing the instances they've been able to secure as they start up, and the blue line showing the number of nodes available to their cluster for submitting their jobs. Thanks to spot pricing, they're able to get all of the capacity they need from advanced, compute-specialized nodes at a cost of only $200. After visualizing the results of their first run, Alice thinks they might get better results by running some of their jobs on memory-intensive instances instead. Alice and Bob decide to quickly experiment with a new instance for some of their memory-bound workloads to increase their simulation's precision. After verifying their experiment was successful, Alice and Bob go ahead and start their cluster once again, scaling this time to 25,000 cores, and then all the way back down within 45 minutes. And because they used EC2 Spot, they were able to finish all 3 of their workload runs before lunchtime at a total cost of less than $1,000. Alice and Bob take a leisurely lunch, finish making all of the necessary changes to their report based on Carol's feedback, and present their updated results before their deadline. While the particulars of this story are obviously fictionalized, they illustrate using real data taken from Amazon CloudWatch what's possible for any one of our customers to do with ParallelCluster in terms of scale, flexibility, and elasticity. No procurement process or special advance notice required. After this presentation, you should be familiar with the basic ideas behind how ParallelCluster works and what it looks like to use it. Once you're familiar with some of these basic ideas, you might be interested in understanding some best practices for working with ParallelCluster, as well as some of the more advanced functionality that's available within it. I'll be highlighting just a couple of areas of particular interest, showing you as well how these areas map to parameters within the text configuration file. While all compute nodes are located within the same availability zone by necessity, you can choose to enable placement groups to ensure that compute nodes are placed even closer together as a way of minimizing inter-node communication costs. If you wish to work with a placement group, you can either set this value to be dynamic, in which case a unique placement group is created as part of the cluster creation process, or you can choose to enable a placement group that you've already created outside of ParallelCluster as well. You can also choose whether you wish to locate only the compute nodes or both compute nodes and the master node together in the same placement group. A key feature that's completely unique to AWS is Elastic Fabric Adapter, or EFA. Just like placement groups, EFA is another feature that helps in minimizing latency and achieving higher throughput between nodes than possible with traditional TCP networking. EFA is a network interface that can be attached to Amazon EC2 instances to bypass the kernel for faster network communication. You can see here the instance types available today that are compatible with EFA and with ParallelCluster. Most applications work with EFA as is, provided a supported version of MPI is used. As of today, that includes both OpenMPI and Intel MPI. Something we have yet to touch on, but that is a critical part of setting up your HPC cluster, is picking and choosing the right instance types to use for your cluster. Because there are more than 190 instances available to pick and choose from in Amazon EC2, you have a wealth of options to match the specific demands of your applications. Some of those characteristics include CPU, number of cores, bandwidth, and GPU. Those characteristics are likely to vary depending on whether you're running ML, CAE, weather modeling, seismic imaging, computational chemistry, or any other number of research applications. But rest assured that there's an instance to suit all of these different kinds of workloads. If you're interested in digging into more of how to think through what instance types and sizes might be most appropriate for your own workloads, I hope to see some of you at the Builder session for selecting the right instance for your HPC workloads. I'll also recommend the AWS white paper, Achieving Optimal Price Performance for Your HPC Workload, in which characteristics of available instances are discussed in much more detail. While it's important to dedicate thought to selecting the right instance type for your compute nodes, it can also be important to think through an instance to choose for your master node. Important considerations to have in mind here are that your master node is responsible for orchestrating the scaling of your overall cluster and running the job scheduler. If you have a big cluster, you may need to select a master node instance that has more compute to manage all of those processes. You might also consider whether to use a GPU-based instance if you are planning to use DCV for graphics-intensive visualization or purposes, since that process is done through the master node. Once you're at the stage of considering how best to manage the cost performance of your HPC cluster, one of the biggest options that you'll have is being able to pick and choose what pricing model is most appropriate for your workloads. ParallelCluster supports on-demand, reserved instances, and spot pricing models. As the name suggests, on-demand is most suitable for workloads that have to be completed right now. For any of your workloads that are fault-tolerant or where you can be flexible in when you want to run them, you can use spot pricing, where you would run your compute nodes using the excess computing capacity available on AWS at a given time. You can achieve savings of up to 90% relative to on-demand prices by using spot, with the trade-off that these instances can be interrupted and reclaimed if that capacity ends up being needed by others. You can use the Spot Advisor to learn more about rates of interruption on your preferred instance types. Choosing between Spot and On-Demand just requires changing the cluster type parameter in your configuration file. Purchasing reserved instances means that you can lock in a guaranteed level of savings versus On-Demand by committing to a level of usage in advance of running your workloads. Once you've purchased those reserved instances, you can leave the cluster type as On-Demand, and the savings will be applied automatically. FSx for Lustre is a new managed file system service released by AWS this year that is based on Lustre, the popular open-source parallel file system designed for compute-intensive workloads. Lustre includes a POSIX-compliant file system that can scale to thousands of clients, millions of IOPS, and hundreds of gigabytes of throughput per second. With ParallelCluster, you can choose to either mount an existing FSx file system you've created, or have ParallelCluster create one for you on the fly, with a few simple parameters in your config file. Because many workloads are not optimized for hyper-threading, in the latest release of ParallelCluster, you can choose to disable it with a simple parameter in your config file. If you wish to bring your own software or specialized operating system setup to AWS, ParallelCluster supports a number of ways for you to bring your own custom AMIs for use in your clusters. You can choose to either install your own software or modify your image configurations on top of an official ParallelCluster AMI. Or, if you already have an AMI you like, you can simply choose to install ParallelCluster on top of it at runtime. With that, I hope you have now a better understanding of the many things that you can do with ParallelCluster and HPC on AWS. While there's much more to learn, I hope you have some ideas for how it is that the cloud can benefit you and the work that you're doing today. Thanks for your time. Feel free to reach out to me personally, Nathan Stornetta, through my email address, stornetn@amazon.com. Or you can always reach out to the AWS ParallelCluster team through our GitHub repository, the link for which is shown below. Thank you.